Welcome back. Welcome to part 8. And in part 8, the fun is going to begin. We're going to begin to systematically and methodically just move through the Intel 8080 instruction set and write the functions that will actually output binary code for each of those instructions. So we'll conclude today with actually implementing our NOPs, our very first instruction, because there's a little bit easier way to subdivide these, but NOP is the easiest and it's the very first instruction, so that's the one that we're going to start with. Two interesting questions arise. One is, well, what exactly is the binary code for each instruction? So NOP would be 00, LXI is 01, stacks is 02, inks is 03, so on and so forth. The other interesting question is, how can we sanity check to make sure that an instruction has the proper number of arguments, right? NOP doesn't take any arguments. LXI takes 2, stacks takes 1. So we need to find a way to check that. So I'm going to actually start by writing that kind of sanity checking function. So we'll say ensure the proper arguments are provided for the instruction. And we'll just call this function check. There's nothing particularly fancy about the naming as usual, but let's do that. So it'll take a number of tokens and that Boolean we're going to call passed, as in not failed. We're going to say if passed equals false, then we should throw a new exception. And the reason we need to send tokens in with check is because in our exception, we're going to say arguments not correct for instruction. And we'll concatenate that with tokens.instruction. That way the user knows. So let's write our very first processing function, which will be NOP. And NOP has instruction code hex 00. So I'm just going to put that there just to remind myself what output I should be getting. All right, so we're going to say, make a new function called NOP. And all of our instructions, if you remember from process, take 2 arguments, tokens and output. So in NOP, it's going to take tokens, and output. First thing we want to do is check to make sure that we have the correct number of arguments, which for NOP should be 0. And so tokens is going to be our first argument to check, since we have tokens here, and that way we can just spit out what the instruction was if it's incorrect. But what goes into this Boolean, this passed Boolean? Well, we can use the logic that is built into D and built into many languages to do that work for us. So if it's the case that we don't want to have any arguments, we can combine the fact that strings, as we learned, has an empty property with ands. So we can say tokens.first.empty and tokens.second.empty. Right? And this will actually check to see, is the first argument empty, is the second argument empty? And so if you have 1 and 1, you have 1, so you would pass. If you have 1 and 0, right, so on and so forth. So we want to actually check to make sure that both tokens for the first argument is empty and the second argument is empty. If for some reason you have a first argument, or somehow you have a second argument but not a first argument, or you have both arguments, pass should become false and it should give you a complaint that the arguments are not correct for the NOP instruction. So after we do that check, we need to perform some sort of action. And that's kind of the way that all of these instruction named functions are going to work. They're going to do a check and then they're going to perform some sort of action. So we haven't written the action function yet, but I'm going to go ahead and write what I know to be our argument. So action is going to take 4 arguments. It's going to take our tokens, it's going to take our output, it's going to take then 2 numbers. In this case for NOP, it's 1 and 0. So let's go ahead and actually write that action function. And then we can actually see how it works in action, no pun intended. So this function will take appropriate action depending on which pass it is. So we're actually deferring, for the most part, what to do for each pass all the way down till we get to the actual action we want to perform. So we'll say tokens, output, and then I'm going to say the third argument is going to be an unsigned short, which will be a size. And again, unsigned short because there is no way an instruction is going to be longer than 65,536 items, because that's bigger than what we could even store in an 8-bit program anyway. And then also say int out byte. And so what do we need to do? Well, we need to do different actions depending on which pass we're in. So first we'll check to see if we're in pass 1. If we are, we'll do one set of actions. And if not, we don't really need to check for pass 2 because there's only pass 1 and pass 2. So we'll just say else. If we're in pass 1, we need to add a new symbol if we have a label. We don't know if we have a label. Well, at this point, we do know if we have a label, but we can't know at the time of writing the code if we have a label, right? Some lines will have labels, some lines will not have labels. But that's very easy to check, and you probably already suspect that you know how to check this. If it's not the case that the label is empty, then we want to add the symbol. Easy as that. That's it. We then need to increment the address counter by the size of the instruction, because we need to make sure that the address for the label actually corresponds to the address where that label shows up in our source code. So we need to know how big each instruction is. And it turns out there are not that many options for how big an instruction can be. It can be either 1 byte, 2 bytes, or 3 bytes. And this table here is actually telling us how many bytes each instruction is. So this number here, it's this left number right underneath the instruction name, tells you how many bytes that instruction is. So for NOP, it's 1, and that's why we put 1 in as our size argument. And an out byte is what byte should actually be printed out, right? What byte does this instruction actually correspond to? And for NOP, it's hex 00, which is why hex 00 went into that 4th argument. So let's do that incrementation. So let's say output.address plus equals size. Simple enough. Now it might be the case that, your address might become larger than hex FFFF. One of your homework assignments will be to detect if address is now too big and throw an error if it is. Again, I'm not going to do it for this workshop, but it's a thing for you to think about moving forward. Do you want the possibility to end up assembling files larger than you can actually address and actually use on such an 8-bit CPU? All right, so that takes care of pass 1. If we're in pass 2, all we need to do is output the byte representing the opcode. But what happens if our opcode takes 3 or 2 bytes, if that instruction takes more than 1 byte? Well, we're essentially going to defer that knowledge and that calculation until later on. So we'll say if the opcode carries additional information, such as an immediate or an address, we will output that in a separate helper function. So for now, all we have to do is use the same magic we've been using before to concatenate something to something else. So we can say our output.exe, we just want to concatenate the out byte, and we'll cast the out byte to a U byte, because if you remember, in our output object, our executable is an array of U bytes. So we'll just cast that into a U byte. And that's it. So regardless of which pass we're in, we will perform the correct action. If we're in pass 1, we need to do a label check. We need to add a label if we have one. No matter what we do, we must increment the address counter by the size of the instruction. That way we know and can keep track of where we are in the 16-bit address space, so the next label we run into can have the right value. If we're in pass 2, we simply spit the byte out. That's all we need to do. And so at this point in time, we actually have, well, I don't know if I'd call it a completed assembler, but you in fact have an assembler that can take any number of NOPs that you write and output the correct number of zeros. On the other hand, being able to output NOPs and only NOPs probably won't make for a very useful set of programs that we can write. Seems like we'll need a little bit more than just NOPs, but we're going to call it for now. We will make sure to commit our work, add check, action, and NOP. And in the next episode, we will implement a full quarter of all of the 8080 instructions. We're going to tackle this section here, all of these moves, and this little halt here. So by the end of the next episode, we will have a full quarter of all of the instructions completed and assemblable. So join me in the next episode, and I will see you there.